A sequence is a function that goes from the natural numbers as a domain, and then the range can be any real number. Actually, sometimes with sequences, we also include 0 in our inputs. That just tells you for a sequence which number in the sequence it is. Normally we start counting from 1, so you'd have like the first term, the second term, the third term, the fourth term, and so on. Sometimes we start counting from 0, where this would be the 0th term, the first term, the second term, and the third term. So that's what a sequence is. It's denoted with these curly braces with the rule inside, where n goes from a starting point, usually 0 or 1, but it could be anything, and then off to infinity. Sequences go on forever. They're an infinite list of terms, as you can see here. So sometimes in general, a sequence is just listed like this, where then we would know to start from either 0 or 1 and then just go on to infinity. So some examples here. When n in this case is 1, we get 2 over 1. And then when n is 2, we get 3 over 2. And when n is 3, we get 4 over 3, 5 over 4, 6 over 5, 7 over 6, and so on. And those would be the terms in the series. Notice that when n equals 1, I have the first term. When n equals 2, I have the second term. When n equals 3, I have the third term, and so on. Some other examples here. This particular sequence will start at 0. It's just because it's the sequence as it's given to us. I could have easily started this sequence at n equals 1 and then adjusted the n's here. So if I started this with n equals 1, then this would have been n minus 1, and that would have just been n. So really we can start a sequence at anything and then adjust the functional rule accordingly. In this case, though, we'll go with what's here. When n is 0, we have that the numerator is -1 and the denominator is 1. When n is 1, we have the numerator is 1 and the denominator is 2. When n is 2, we have that the numerator is again -1 and the denominator is 4, and then 1/8, and then -1/16, and 1/32, and -1/64, and 1 over 128, and so on. And normally we would simplify these, especially if we're looking at rules and patterns. This is really just -1. And then we notice each time what we're doing is we're just dividing the term pretty much by -2. So to go from the first to the second, I divide by -2. From the second to the third, I divide by -2. From the third to the fourth, I divide by -2. Just as an aside, that's called a geometric sequence. You did do those very briefly in Algebra 2. I don't know if you remember or not, but that's in the side. Not all of the rules have to be expressed algebraically or arithmetically. As you can see, this particular sequence here represents a list of digits where each one is a digit of pi. So this would be 3, 1, 4, 1, 5, 9, 2, 6, 3, and so on. And again, there's no nice way of writing that rule, so we can write it out as simply the kth term in my sequence, b sub k, is equal to the kth digit of pi. The first digit of pi is 3, and the second is 1, and the third is 4, and so on. So now we have a definition, and definitions in quotes, because this isn't the real definition, it's more of an intuitive thing. Limit definitions aren't in the curriculum anymore. Maybe after the AP exam, if we're continuing with this, I'll do a lesson on that. But here we say that a limit, as n approaches infinity, of a sub n is equal to L, the limit of a sequence is L, if and only if the terms of that sequence eventually get infinitely close to L. And here we have eventually. So if the sequence goes crazy at the very beginning and then it stops and then gets closer, then we're fine. We can chop off as much of the beginning of the sequence as we want to examine the limit. Just as long as it eventually gets close to L, then we'll say that the limit exists. If L exists, we say that the sequence converges to L. Otherwise, the sequence diverges. So some examples. In this case, if I want to find the limit as n approaches infinity of this sequence, what I do is I just look at what happens to these terms. Well, we know how to do these kinds of limits. If x were a real number, we'd be able to find this limit. And since natural numbers are a subset of the real numbers, if we're going to infinity, these are going to act pretty similarly. Not always the same, but for the most part, we can make that conjecture. So here as n goes to infinity, this is just going to go to 1. So this sequence converges to 1. This particular sequence, limit as n goes to infinity, -1 n plus 1 over 2 to the n. Well, I have these terms here, and if you notice, they kind of bounce around, but as they bounce around, they get closer and closer to 0. this limit winds up converging to 0. And we could actually use the squeeze theorem to prove that if we wanted to. The numerator is always going to be between -1 and 1. So this would be the same as looking at it between -1/n and 1/n. Both of those go to 0, so this goes to 0. Here, n starts at 1 and goes to infinity. So what is this? Well, here I could examine as n goes to infinity of n, which is just infinity. And sure enough, this diverges. If I write the terms of this sequence out, it's just the natural numbers. And the natural numbers never approach anything. They just grow infinitely large. Number 7 is one of the rare examples where we can't really treat this like we would real numbers. We know that the sine curve, if we were to graph it, looks like this. And as x goes to infinity, this bounces around. It oscillates, so it doesn't have a limit. But if we examine what happens with just the sequence of terms, when n is 0, sine of 0 is 0. When n is 1, we have sine of pi, which is 0. When n is 2, we have sine of 2 pi, which is 0. And then sine of 3 pi and sine of 4 pi and so on. This limit actually exists. And this limit, since n is only a natural number or 0, winds up being 0. This converges. This function does not converge as x goes to infinity for real numbers. But if we're dealing with a sequence of terms, these converge to 0. It's just a constant sequence. Here, this is interesting. As n goes to infinity, what happens here? Well, this is going to keep bouncing around. But as n goes to infinity, this inner term winds up getting smaller and smaller and smaller and starts acting like 0. And we've seen this before. So as this inner term gets closer and closer to 0, the sequence terms will get closer and closer to 0 because the sine of 0 is 0. Unfortunately, there's no nice way of doing this computationally. I can't pull the limit inside because sequences are not continuous. Remember, if we're graphing them, they're only where the natural numbers are. So sine of, well, when n is 0, I should really start this at 1. N can't be 0. When n is 1, this is sine of pi. Sine of pi is 0. And then we have sine of pi over 2, which is 1. And then we have sine of pi over 3, and sine of pi over 4, and sine of pi over 5, and sine of pi over 6, and sine of pi over 7, and sine of pi over 8, and sine of pi over 9, and sine of pi over 10, and sine of pi over 11, and so on. They're not connected. It's discontinuous. So these terms do go to 0, but I don't have any nice way of pulling the limit in. I just kind of have to do this intuitively. And this is an example where we talk about the eventually getting infinitely close to 1. So this sequence starts out going 1, 2, 3, 4, and it does that up until 999. And then once k is 1,000, it's just a bunch of 5s over and over and over again. And you'll notice if we keep going, eventually there will be so many more 5s. This is irrelevant, the very beginning of this sequence. So we can just kind of not ignore, but since we're only dealing with n getting infinitely large, we can disregard that. And this sequence actually converges to 5. So this converges as well. And that deals with the eventual convergence, like I was saying before. So those are some examples of sequences and their convergence. Some important concepts involving sequences involves how do we know if they converge and what kind of sequence is it? Like, what can we say about the terms? So first of all, some things we can do when we're taking the limits of these sequences. If we have two separate sequences and we have some number in the sequence that's a natural number, so this is some element in the domain. And what this n represents, it represents the eventuality. So like, think of the big N as where the sequence starts to exhibit the behavior of convergence. So in that last example, it would be the number 1,000. It could start off that way, but this is just a nice way of mathematically saying eventually. So if we have a specific value that we can set up where if I add the corresponding terms, I get another term for all n greater than n. In other words, if when I add the two terms of the sequence, I get this other term eventually, then the limit of the new sequence will be equal to the limit of the sum of the old sequences. In other words, the limit of the sum of the sequences is the sum of the limits of the sequences. And again, this n just represents the idea of eventually. So like if I have two sequences and they're kind of bouncing all over the place, and then all of a sudden, after a certain point, then they start to act like, okay, now when I add them up, now I get this third sequence, then this applies. And that's what that n kind of represents. The limit of the difference of two sequences is equal to the difference of the limits. The limit of the product of two sequences is equal to the product of the limits. And the limit of the quotient of two sequences is equal to the quotient of the two limits. Of course, as long as the limit of the second sequence is not 0. And of course, this would also have to be where the b sub n's are not 0, because otherwise it wouldn't make any sense. And then finally, if I have a constant in my sequence, I can just pull it out when I'm evaluating the limit. So these are very similar to the limit theorems that we have for real numbers, just dealing with them as far as sequences are concerned. And then we have a squeeze theorem for sequences as well, and this is the one I was talking about before. We know, just as an example, that, negative 1 to the n plus 1 will always be greater than or equal to negative 1 and will always be less than or equal to 1. And that means that the terms in this sequence, will always be stuck in between negative 1 over 2 to the n and 1 over 2 to the n as these bounce back and forth. So we know that the limit as n approaches infinity of negative 1 over 2 to the n is going to be 0. And we know that the limit as n approaches infinity of 1 over 2 to the n equals 0. Therefore, the limit of this sequence here, limit as n goes to infinity of negative 1 to the n plus 1 over 2n, will also be to 0. So this converges to 0 by the squeeze theorem. And now here's the other interesting thing. If we have a function, a real valued function, where all of the elements that are defined by natural numbers in the domain are equal to the elements of the series, or rather the sequence, then I can just look at the limit as x approaches infinity of the real valued function. So just as an example here, does this converge? Well, I don't know. And I could try numbers like when n is 1, this is e. When n is 2, this is e squared over 4, e cubed over 8, e to the 4th over 16, e to the 5th over 32. And it's kind of hard to say whether or not this is going to converge or not. So what we can do is, instead of looking at this, we can consider the function f of x equals e to the x over x squared. Now, if this diverges, then my original function will diverge. And that's what this says. Basically what it's saying is, if the real values diverge, they don't approach anything, they shoot up or they shoot down, then if I just look at the points along it, so like if I have a function like this, and this is obviously diverging, it's going off to infinity. If I just look at the points where the natural numbers are defined in the domain, then they're also going to shoot up. Note that this does not work for convergence, it only works for divergence. And a counterexample for convergence would be this example here, number 7. The limit as x approaches infinity of sine pi x diverges, because it oscillates, it doesn't go to infinity. So just because a function diverges doesn't mean that the sequence diverges. It has to actually go to infinity or negative infinity. And just because a sequence of real numbers converges, or rather just because a function converges, doesn't mean that the sequence will converge. That's because we're taking things out of it. But anyway, the example here is, does this converge? Well, I have to check the limit as x approaches infinity of e to the x over x squared. And we know that we can use L'Hopital's rule to check this, because the numerator and denominator are going to infinity. And then we can use L'Hopital's rule again. And finally, we note that this winds up going to infinity, because the numerator goes to infinity, the denominator goes to 2. So does this converge? No, it doesn't. In the event that this limit existed, I would not be able to make a conclusion about whether this sequence was convergent or not. So all I can do when I'm talking about sequences diverging is looking to see if the real valued function approaches infinity or negative infinity. It's a rare example when you would use this. It does help on occasion, though. Okay, So the last thing we have to look at is talking about sequences that are increasing and decreasing. And this is going to come into play because we have certain types of sequences that we can actually prove converge or diverge based on if they're increasing or decreasing. So let this be a sequence. If the current term in my sequence is always less than the next term, then we say the sequence is increasing, and that makes sense. If the current term is less than the next one, that means the next one is bigger and my sequence is getting larger. Similarly, if the next term is larger than the current one, then, if the current term is greater than the next one, then the sequence decreases, because that means the next term will be less than the current one, and my sequence will be decreasing. If either of these conditions is true, eventually, this just means eventually, then the sequence is either eventually increasing or eventually decreasing. And again, that concept of eventually is important because when we talk about if a sequence converges or diverges, we don't care about what's happening at the beginning, only what's happening at the end. So from this theorem, or from this definition of increasing and decreasing, we can actually come up with a theorem for determining whether or not a sequence increases or decreases. So remember, a sequence increases if the next term is bigger than the current one, and a sequence decreases if the next term is less than the current one. So what would happen if I took this and I subtracted a sub n from both sides? Well, I would get this. And sure enough, this is the definition of a sequence increasing. So if I subtract a sub n from both sides, I wind up with this inequality. If this inequality is true, my sequence increases. Similarly, if I subtract a sub n from both sides of this one, I get this inequality, and that means my sequence decreases. We could also divide both sides of this inequality by a sub n. And if we divide both sides of this quality by a sub n, then we get this inequality, which means my sequence will be increasing. If I divide both of the sides of the inequality by a sub n over here for my decreasing sequence, I get this inequality, which means both of them are decreasing. And then the last thing we can do to determine if something's increasing or decreasing is look at the actual function itself. If the real valued function winds up increasing, meaning the derivative of the real valued function is positive, then the sequence is. And that's because what we're saying is, well, if I have a real valued function that's increasing and I look at just specific points on it, like this, well, since every later point has to be bigger than every earlier point, then it doesn't matter if I look at them continuously or if I just start picking them left to right. As long as the function is increasing, so too will the sequence, and the same with decreasing. And so for these, we can look at the derivatives. So just some examples here. If I want to determine, is this sequence increasing or decreasing, I've got three different ways of doing this. I can examine whether or not a sub n plus 1 minus a sub n is greater than or less than 0. So in this case, what is a sub n plus 1? A sub n plus 1 is n plus 1 over n plus 2. A sub n is n over n plus 1, and now I need to determine, is this greater than 0 or is it less than 0? Well, let's keep playing with this, doing a little bit of algebra to get a common denominator so I can determine if this is greater than or less than 0. Here we have n squared plus 2n plus 1 over n plus 1, n plus 2. Here we have n squared plus 2n over n plus 1 times n plus 2. And then if I subtract, I'm left with 1 over n plus 1, n plus 2. And now it's important to remember that in sequences, the n will always be a natural number or 0. That means this term will always be positive, and this term will always be positive. The 1 is always positive, which means this is positive, which means my sequence is increasing. We could use the second test to determine if this is increasing or decreasing. We can look at a sub n plus 1. That's n plus 1 over n plus 2. We can divide it by a sub n. That's n over n plus 1. This would be the same as n plus 1 over n plus 2 times n plus 1 over n. That's the same as, if we multiply this out, n squared plus 2n plus 1 over n squared plus 2n. And this is going to be greater than 1. Now, how do I know this is greater than 1? Well, that's because n squared plus 2n over n squared plus 2n equals 1. And I'm adding an extra 1 on top. So if I'm adding something additional to the numerator is always going to be larger than the denominator, which means this is always going to be greater than or equal to 1. So this is increasing. So it's important that you have a good sense of numbers and arithmetic and algebra here so that you can make a conclusion. Well, since this term, n squared plus 2n over n squared plus 2n is equal to 1, if I add anything else to the numerator, I'm going to get something greater than 1. And again, 1 is positive, I'm adding something positive. The third test we can do, and again, we only have to do one of these. I'm just doing this to demonstrate all of them. The third test that we can do is we can look at the derivative. So in this case, let's assume that we have a real valued function, x over x plus 1. Let's examine the derivative of this. Bottom, derivative of the top, minus top, derivative of the bottom, all over the bottom squared. And that would be equal to x plus 1 minus x over x plus 1 squared. And that is equal to 1 over x plus 1 squared. X plus 1 is a real number in this case. And when I square it, I get a positive number. And 1 is a positive number. So if we examine this for just natural numbers, since we're in a sequence, I wind up with this term. And this term is always going to be positive. Well, that means my derivative is always positive, which means my function is increasing. So all three of these tests have independently shown that this sequence is an increasing sequence. And that's something that is incredibly important because that's something that's going to come into play when we look at whether or not increasing, decreasing sequences, also called monotonic sequences, converge or diverge. So anyway, that is it. This lesson was just okay. It wasn't great. I feel I stuttered a little bit. I hope I got everything across. So I'm going to give this lesson a B. So you're going to get my seal of approval, B style. And that's it.